All right, so here in our third podcast for our kinetics unit, we're going to be starting to talk about mechanisms and mostly some important vocabulary on page 21 to do with these mechanisms. And it's not even all of page 21. That top problem is actually a holdover from the individual practice problems that you should be working on. And we're going to stop before we get to those steady state approximations at the bottom. Like I said, mostly some definitions and just some practice applying these definitions. So first off, a reaction mechanism is what we call kind of the recipe, the multi-steps reactions broken down into their steps. So a reaction mechanism represents the sequence of bond making and bond breaking steps that occur during the conversion of reactants to products. Sometimes these happen in one step, sometimes they happen in more than one step. It's important to know that we can't actually prove a reaction mechanism absolutely. We can only come up with a possible mechanism, and then once we have an idea of what might be happening, what chemicals we might be forming as some of these intermediate steps, then the mechanism has to be determined. We can only be 100% confident in it once we do an experiment and actually prove we actually did make certain chemicals. So after we use that experiment has to agree with the overall stoichiometry of the original reaction and with the experimentally determined rate law. So some of these things are not super realistic, but they are a possible mechanism, a possible path that can happen, and we have yet to prove that that's not the way it happens. And this is a very kind of emerging or very active side of chemistry, trying to figure out some of these intermediate steps, because these are the ways that we can help speed up some of these reactions the best, make them more efficient, make more money in a shorter amount of time. And that's all what that big business cares about these days, it seems. So getting into some of the vocabulary. An intermediate, I've used that word a couple times now, is just kind of an in-between step. And a chemical intermediate is a chemical species that's neither a product nor a reactant in the overall equation. It's made during the course of the reaction, and then it gets used up before the end of the reaction. So it only exists there in the middle of the reaction, which is why it's called an intermediate. It's important to know that intermediates are never going to be included in the rate law. Remember, we only include the reactants in the rate law. So if these aren't reactants, they're never going to be included. Catalysts are similar but different. Catalysts go in. They are reactants, but they're also reproduced or unchanged as a product. So these generally don't show up in our rate law unless they're a homogeneous catalyst, meaning they affect the concentration of the other substances. So if we look at this example here with all of my NO chemicals in this first step of the reaction, and then we have the second step of the reaction, we can tell that NO3 is an intermediate because it is a product of one of our steps, and then in the next step it gets used up. So as we're starting and finishing, we don't start with NO3, we don't finish with NO3, but it is present during the course of the reaction. So it's involved, but it's an intermediate. And then our NO2, or at least one of these NO2 molecules, technically counts as a catalyst because it's used up in making the NO3 and NO, but then it is reproduced there at the end of this reaction. So it's not actually completely used up, it's just used to help cause a collision, get that NO3 made, so that then we can create that CO2 and NO2. So that is a catalyst because it started there and it ended there, but it was not used up in between. And if we kind of cancel out these intermediates and catalysts, anything that shows up on both sides of the reaction, it's getting used up. It's not part of the overall reaction. So if we cross those out, cancel those out, the real overall reaction is going to be made from combining what's left from each of these steps. So our real overall reaction here is NO2 plus CO, make that look more like an O, turning into CO2 plus NO. That's the overall reaction that's occurring here. We've just broken that down into two steps to show the process of the reaction, because the NO2 and the CO don't actually react together. It ends up being the NO3 and the CO, and we have to have two of those NO2s there to actually form that NO3. So probably getting a little bit too involved in this example that's not even written in your packet, just trying to show you a little bit of what's going on here. Getting back on track, talking about a few more definitions. This is a really important word to notice. Elementary. It's either an elementary step or an elementary reaction. And these are reactions or steps where the rate law can be written based on the molecularity of that step or of that reaction. And molecularity is the number of species that are colliding. So basically, the stoichiometry, the number of things that are colliding in that reaction. I've told you over and over again with the previous two ways that we found rate laws that you do not care about the stoichiometry of the reaction. They could have 2s and 3s up there and everything could be first order or zero order. So the reaction doesn't usually matter unless it's an elementary reaction or an elementary step in a reaction mechanism. If they tell you that it's an elementary reaction, it doesn't just mean it's simple. It means we can use that stoichiometry, the balanced numbers in the front of the reactants, to create the rate law. And that is a huge time saver. Now, just some special versions of that molecularity word. Unimolecular, meaning one molecule, is a reaction or a step involving only one molecule. And that molecule is either going to break up after it collides with something like a solvent or a background molecule, or it's going to kind of react with another molecule of the same kind. So it's just, or sorry, it has to be involved with a background molecule. There always has to be a collision that happens. It just might not collide with another reactant molecule, basically. Bimolecular steps are reaction steps involving the collision of two molecules, hence bi. And if that happens, the rate law is always second order. And you can have trimolecular steps or polymolecular steps, but these are just kind of prefixes that we are already familiar with being added onto these molecularity of each step there. Another very important word down here is the rate determining step. The rate determining step is the slowest step of a reaction mechanism. Think of this like a group kind of trying to get through their work. The slowest person is going to determine the rate that that group can go. Because the fastest person can go fast, but if they leave everyone else in the dust, then it's like the slow people are still determining when the group is done. So if you bring those slowest people along with you and you help support them, then you can maybe get done faster. But it's always going to be based off the speed of the slowest person in your group. And for chemical reactions and writing rate laws, we can use the stoichiometry of the reactants from the rate determining step to write the rate law. So that's like our elementary reaction. We are allowed to use that stoichiometry, just the numbers in the balanced equation, to create the rate law if we have a rate determining step in our mechanism, because it is allowed to determine the rate. So if we have some fast steps and one slow step, that slow step is what we call the rate determining step, and we can use it to write our rate law. And we're going to see that here in just a moment. So we kind of mentioned this up in that top paragraph as we started, but a reaction mechanism, this kind of sequence of steps, always has to add up to the overall equation. So the actual chemicals have to be the same chemicals, and they have to be in the right amounts to add up, cancel out, or combine to form that overall balanced equation for the reaction. And they have to agree with the rate law. Now, we'll get to some fancier mechanisms in a moment, but just coming back to that idea of an elementary reaction, that means that we can use the stoichiometry of this balanced equation, and it is balanced here, in order to write our rate law. And remember, our rate law is rate equals K times our concentrations of our reactants, so NO and N2O, still only reactants, raised to some power. And here, because it's an elementary reaction, we can just use the stoichiometry, the numbers from that balanced equation, which if there are no numbers, then those are ones. And similarly, we can either just leave those blank because it's understood to have ones there, or you can actually write the ones, just like I recommend you kind of do in the reaction and in our rate laws. So that's our rate law. It's that simple if it's an elementary reaction. This next example is a reaction mechanism. We've got 2 steps, but they tell us about the speed of those steps, and one of them is slow and the other is fast. So the slow one is our rate determining step, which means we should be able to use the stoichiometry of that step, specifically of the reactants, to write our rate law. So just like the last one, rate is equal to K times the concentration of our reactants raised to the exponents, which here we would use the stoichiometry, the balance coefficients, when this is balanced. So those are each ones again, which I know these are pretty simple examples, but we can't normally do this. Normally we have to do a whole lot of work comparing trials or comparing rate data in order to be able to find these orders. But with a mechanism, that's really the advantage to us having a mechanism for a reaction, is we can break it down into simpler steps and we can know more information about the overall reaction based off of those mechanisms and those steps. So that's it for now. We'll talk more about that steady state approximation in class.